This video might be a little bit provocative to some atheists and perhaps even some theists who follow my channel, so welcome. I want to talk about a rhetorical device that comes up in debates between theists and atheists, and it'll go along the lines of, the theist will say, oh, well, you know, you atheists have faith too. And very commonly, an atheist will respond by saying, oh, no, 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 I don't have faith. The argument to be had there doesn't lie in denying that you have faith. The argument to be found there lies in equivocation. There are multiple definitions of faith, and what is meant by faith in the religious context is not what is meant by faith in this other definition, this more banal definition, this more casual definition of having trust or confidence in the veracity of some propositions, or trust and confidence that something will work out a particular way. Like, if you drop a ball a million times and you see it does something, it's reasonable to be confident that if you drop it 1,000,001 times, the 1,000,001st dropping of it will operate just how it did the 1,000,000 previous times, or very similar to the 1,000,000 previous times. So you have faith at that level, just having trust or confidence, which can come from logic, it can come from reason, it can come from science, it can come from empiricism, things of that type. There's a reason other than you want it to be true, or other than you just believe it to be true, to believe that it is true, to be confident that it is true, and that is a type of faith. What is meant by faith in the religious context is that it is the adherence to some religious dogmas, or the religious-like attachment to the truth of some propositions involving the existence of a deity by some definition, by some description. So what is really operative there is what is being packed into the label faith. Okay, now expanding out from that a little bit, I'm pretty sure that some of the atheists watching this will say, "Oh, but no, actually, I don't have faith at all. There are good reasons for me to believe certain things based on science." The problem there is that what undergirds science is a series of assumptions which aren't known to be true. They are just taken to be true because it is useful to assume that they are, and after you make that assumption, you don't question it anymore. You just go on doing the enterprise of science. But if you don't accept those assumptions as true, then you can't really do science in the way that we understand science. So I'll give you one. One of them is the so-called law of uniformitarianism. There is no reason at all to believe that this law is true. For those of you who don't know, the law of uniformitarianism states that the physical processes that operate in the universe today are the same physical processes that operated in the universe for all of its past, will operate in the universe for all of the future, and operates everywhere in the universe without variation. There's not even in principle is it possible to show that this is true, and I'll try to explain why. One reason is we don't live in the future. We won't live for infinity, so not even in principle can you test whether or not the ones in our local region of space will be operative for all time. But even more than that is that we can only see so far into the universe. We are only causally connected up to the light bubble of the universe. That is, given the age of the universe, our local region of it anyway, how far light has traveled in the time that's been available, taking into account the expansion rate of the universe and things of that nature, there is a hard wall beyond which we cannot see. However, there are objects that are in the universe today, in the observable universe today, that weren't in the, there are objects not in the observable universe today that were once upon a time in the observable universe. And it is rank speculation to suppose that the laws of physics, the rules by which the unobservable universe operates, are exactly the same as the rules by which the observable universe operates. That is to say that when a star or a planet or whatever passes that light bubble and goes off into the unobservable universe, for all anyone knows, it could turn into a giraffe, it could blow up, it could disappear. You don't really know, and you can't possibly find out. We just assume that it is the case that at that barrier, things aren't radically different, so the planets that existed on this side of the light bubble today and will be on the other side of it tomorrow will still exist on the other side of that tomorrow in the same way they existed here, just we will no longer be causally connected to them. That's an assumption. You just have to take that as true. I hasten to add, it is not in principle possible to show that that is indeed the case. It is an assumption. We have not the slightest bit of evidence of anything that happens on the other side of the light bubble of the universe. We don't have the slightest bit of evidence as to what is going to happen in a million years' time. Now, some people are probably going to say, but we've done all these empirical tests, and they confirm over and over and over again this is how the universe operates. This is nonsense. The models that attend science are updated. They are changed to take account of phenomenon that are operating in the universe that we see that we didn't previously see. Equally consistent with that observation that there's something happening now that wasn't happening yesterday, such that we don't have to change a model, you could say either of the following. One, the universe operates by some rules which are inviolate, and we just failed to notice it. We weren't looking in the right direction. The diagnostic sensitivity of our equipment was poor. There was a measurement error. There was a theoretical problem, something of that nature. Or you could also say, actually, the rules by which the universe operate changed. And now we have to change our model to accommodate the new rules by which the universe is operating until such time as it changes those rules again, which we might find out in the future or not. We prefer the former position to the latter position because it makes reasoning about this universe much more sensible than saying, well, it actually could be the case that the reason this experiment worked differently than the experiment that was the same kind of experiment that was done last year isn't because there was a problem in the protocols or a problem in the measurement. No, the universe actually just changed. So the result we recorded last year actually really did model the universe at the time, and this new experiment really does model the universe at this time, and the universe operating in this time is operating differently than it operated in that time. It makes the whole enterprise dodgy. So we prefer the one assumption to the other because it makes reasoning more sensible. Now, as a matter of logic, some people will say that, I've heard this, that there are objective, logical truths that would exist in any universe. That's not the case. There is nothing that obligates the universe to follow any rule of logic, and indeed we've discovered certain rules of logic that, with the understanding of quantum mechanics that's come about, we know they aren't actually operative everywhere in the universe, so those had to be dealt with and develop a new system of logic to take account of the fact that, notwithstanding our rules, notwithstanding our having written down on a sheet of paper some rules of logic that the universe should, if it's going to be sensible to obey, it nevertheless refused to obey those rules, so we had to change. The universe didn't. There's no problem with the universe, the existence of a universe that disregards the law of non-contradiction or the law of identity. There are tremendous problems that would exist in that universe for people trying to reason about that universe, but that's a problem for the people trying to do the reasoning. That's not a problem for the universe. If it happens to be the case that there exists a universe where one thing can simultaneously be itself and not itself, so much the worse for people who want to reason about that universe. If those are actually the rules by which it operates, those are the rules by which it operates, and nothing that we say is going to change that. It will be tremendously difficult to reason about that universe, but again, I point out, that's a problem for people who want to reason about it. It's not a problem for the physical processes in that universe. Okay, so just on to take this a little bit further here, a lot of people want to talk about Occam's razor. That's one of the reasons that we take the assumptions that we do. One of the things I don't like about the way people commonly use Occam's razor is they'll say things like, what you should do is keep the least number of assumptions, things of that nature. I prefer Einstein's razor to Occam's razor because it makes explicit something that is implicit in Occam's razor, particularly when you give it that casual definition. And Einstein's razor says this: make everything as simple as you possibly can, but no simpler. Occam's razor says don't multiply beyond necessity entities. Don't add in more assumptions than you require, which a lot of people translate that to mean just make as few assumptions as you can get away with. Or another way to put it, lex parsimoniae, is that if you have two models, each model perfectly describes whatever it is you're trying to model. They both describe how the universe operates in the sense that's relevant. But one has 7 propositions, and one has 6 propositions. You should prefer the one that has the 6 propositions to the one that has 7 propositions. However, if you have another model that only has 5 propositions but fails to account for something, you do not prefer the model that has 5 assumptions to the model that has 6. And you prefer the model that has 6 to the model that has 7, because in the model that has 7, there's one proposition that is superfluous. It's not doing any work there. So Occam's razor, cuts that away, but Einstein's razor just makes it quite clear. Go with number 6 because it's the simplest model, and it's not any simpler than it needs to be to nevertheless model whatever it is you're trying to model. So there's that, and I guess in my next video I'll talk about the whole concept that you can't disprove a negative, that kind of thing. Anyway, I'll see you then. Have a great day.